Professor, I think you're on mute.
My wife must have busted in here somehow.
Yeah, you've been on mute for the past 5 minutes. I don't know if you've been talking or not.
Oh, okay. No, because I signed out of the one and then I had to sign into the new. So. Yeah.
Okay. Okay.
Yeah. Usually my wife doesn't censor me until I've actually been talking for a little while. Okay, so should we just have a question answer thing, or should I start from chapter 10 or something? What would you like to do?
I have a few questions, but maybe we can start with you going through the chapters, and I can ask them periodically.
Okay, sounds great.
Thank you.
So I'll start with chapter 10. And so I broke it up into different parts, right? And at the end, we're doing all the parts all together. And I use water as an example to show all the different parts. And so, yeah, what's really important is you look at this right here. Okay, how many regions of electron density at that central atom? Well, there's 1, 2, 3, 4 regions of electron density. They're going to be as far apart from one another as possible. And that's what gives rise to the tetrahedral shape. But then, this tetrahedral state stays the same, but I don't have atoms on 2 of those regions of electron density. And the X-ray diffractometer does not see the electrons. It sees only where the nuclei are. So what's visible to that machine is that the shape of this is bent. But the only reason why it would be bent is because of those non-binding electron pairs. So that's why we start counting up the number of regions of electron density. And we can also see that it's a bent shape, it's not symmetrical. And then when we apply the difference in electronegativity, we see that the oxygen to hydrogen bonds are polar covalent bonds. That means that they affect properties of the molecule. The electrons are not shared equally. So electrons are being pulled from the hydrogen towards the oxygen, leaving a partial positive charge on the hydrogen, putting a partial negative charge on the oxygen. But instead of having a negative charge on the oxygen atom, which would make it look like it's right there on the nucleus, we usually move it out into a p orbital. And you got 2 p orbitals right here that are not bonding. So that's where we put the negative charges. So we see that, yeah, go ahead.
I have a question there. I just wanted to clarify that for that bent shape, if it's 4 REDs, then the angle is 109.5. But if it's 3 REDs and bent, then it's 120, right?
Exactly. Mm-hmm.
Okay, great. Thank you. Oh, and with regard to symmetry and bonds, if an atom is asymmetrical and it has nonpolar bonds, it's still considered a polar molecule?
No. If you don't have any polar bonds, then it's never going to be able to be a polar molecule.
So if it only has nonpolar bonds, then it will only be able to be a nonpolar molecule?
Exactly. Yep.
Even if it's asymmetrical?
Right. Mm-hmm.
Okay.
Yep.
And then if it's symmetrical, but it has polar bonds, then it's a nonpolar molecule?
Exactly.
Okay. Okay, great.
Like carbon dioxide was an example of that, right? So to be a
Yes.
polar molecule, you have to have polar covalent bonds and you have to be asymmetrical.
Polar bonds and asymmetrical, right?
Yes, exactly.
Okay. It's it gets confusing. I just want to make sure I'm clear on it.
Yeah. Well, if you would just stop being confused, then I'd be very happy.
I know. I got a big problem.
Yeah. No, it's not big. We'll just deal with it.
Right.
Anyway, so then I went through part A in a lot of detail. And so several examples here. And occasionally you might have to make a double bond, maybe even a triple bond, rarely, just to satisfy the octet rule. Okay, so if you look at what we did for formaldehyde here, first of all, the central atom could have been carbon or oxygen. So then I had to go with which one forms the most number of bonds. Carbon forms 4, oxygen forms 2, right? So that's what I predicted. Then I had to count up all the valence electrons, put them in there, first into the bonds, then to the outer atoms. But then I'm not happy until every atom is happy. So I end up having to share electrons from the oxygen to the carbon, making a double bond so that carbon also had 8 electrons around it. So in formaldehyde now, the hydrogen is happy because it's got 2, and that is called the duet rule. And it's happy because carbon went from 1s1 to 1s2, like helium. So it's claiming to have 2 electrons of its own. Oxygen has 8, so does oxygen, carbon. Okay. And then we get to ionic compounds, then we know that there's an ionic bond in there. So for example, this right here represents the ionic bond between the magnesium ion and the chloride ion. We see that from the formula, right? That's an ionic bond right there. And some people might try to make their own polyatomic ion with 2 chlorine atoms, but that does not exist. You've seen all the major polyatomic ions and, very fleetingly, most of the others. Cl2 is not a polyatomic ion. So what you have is 2 monoatomic ions. So I'm putting the monoatomic ion in there. And chlorine is in group 7, but that -1 means it got 1 more electron from somewhere, and that should add up to be 8, so that chlorine is meeting the octet rule.
Excuse me, Professor.
Yeah.
With regard to calculating Lewis structures for covalent bonds, I just wanted to confirm that in a compound, most atoms must complete the octet rule, and that's why they form bonds with other molecules, other atoms.
Right.
But at the same time, they have their own atoms which do not exceed their own valence. So, for example, in nitrite, NO2, I see that N it's in group 5, so it has 5 valence electrons. But it satisfies the octet rule because it has those bonds with O2. So I guess what I'm trying to say is these atoms have to satisfy the octet rule, but they can't exceed their own valence shell for their own electrons. Is that correct?
Wow, you sure made that sound complicated.
I guess, Yeah, I get confused because
Be
when
an
I'm
excellent
solving,
chemistry professor. You'll be able to confuse a lot of students and get paid for it.
I'm sorry, I don't mean to. Um,
So if you follow the procedures, right?
yeah, yeah,
As it turns out, all the electrons, we count up all the valence electrons. It doesn't matter where they came from, what atom they came from.
right.
And the idea is that every atom, no matter what, whether it's in a covalent compound or whether it's an ionic compound, every atom will try to become like a noble gas if it can.
Yes.
It does not care how it does it. It might have to form a double bond or a triple bond. It might have to form an ion, right, to get the right number of electrons. And why does it want to do that? Because that's chemical stability. The octet rule represents S2P6. It doesn't care where it gets it. So for example, you've seen carbon here forming covalent bonds in a polyatomic ion. You've seen carbon form ionic bonds. I mean, it just does whatever it wants to do, whatever it has to do. It's like they're desperate. Atoms are desperate.
I just maybe I should just simplify it for myself and just think that no matter what, unless it's an atom that needs to satisfy the duet rule, I just need to make sure that that central atom has 8 electrons.
Exactly, all of them, every atom.
Okay.
Yeah.
Which atoms satisfy the duet rule besides hydrogen?
Hydrogen, helium, lithium, beryllium, and sometimes boron.
Lithium, beryllium, and boron, you said?
Mm-hmm.
Okay.
Yep.
Thank you.
Only the babies. So then getting the shape, these are diatomic, right? There's no regions of electron density because there is no central atom. So the possibilities for chemistry 100 are simply 2 reds, which gives you a linear, like carbon dioxide, 3 reds, which gives you planar trigonal, like, for example, carbonate, and 4 reds that give you tetrahedral. For example, here, right? So those are the only possibilities that you have to deal with. These other ones in red do not meet the octet rule, so I'm not bothering you folks with it. The biochem students, I bother them with it. And then here's what happens if you start taking a model and you break it down. So for example, linear, let's see. Let's do this one, for example. So this would be linear, right? That black central atom has 2 regions of electron density. Now, if I take one off, it simply becomes diatomic. We don't count non-binding electrons, right? There is no central atom, so it's simply diatomic. Then, if I have something that's planar and trigonal, we just use this, I guess. Okay, that's planar trigonal. The bond angle is 120 degrees. If I take one off, it's bent. If I take off another one, then it's simply diatomic again. Okay. And if I have 4 regions of electron density, then it's tetrahedral. Bond angle is 109.5. And if I take one off, now it's pyramidal. If you take off another one, it's bent. Take off another one, then it's going to be diatomic. While I'm doing this, I think I'm going to do this. So this is symmetrical, right? Because all the white atoms are the same. Symmetrical. A nonpolar molecule. When I take this one off, it is no longer symmetrical. So if these are polar bonds, it's a polar molecule. If these are nonpolar bonds, it's a nonpolar molecule.
Can you repeat that one more time? If it's polar bonds and it's asymmetrical, it's a polar molecule?
Exactly. Right.
Polar bonds,
So
asymmetrical.
if these are polar bonds, this is a polar molecule. If they're nonpolar bonds, there's no rockets, so it's a nonpolar molecule.
Oh, hold on one second. If it's asymmetrical and nonpolar bonds, then it's a nonpolar molecule.
Exactly.
Okay.
Right. So what about this one? It's not symmetrical, is it? It's bent. So again, if these are polar bonds, it's a polar molecule.
Yes.
If these are nonpolar bonds, it's a nonpolar molecule.
Right.
Now when I get to
And if
diatomic, I got only one bond. It's not symmetrical, right?
Right.
If this bond is polar, it's a polar molecule. If it's nonpolar, then it's a nonpolar molecule.
So if it's asymmetrical with polar bonds, it's polar. If it's asymmetrical with nonpolar bonds, it's nonpolar. But what if it's symmetrical and polar?
If it's symmetrical and polar,
Polar bonds, I mean.
everything is going to cancel out.
And therefore it's a nonpolar.
So this is symmetrical.
Yes.
If these are polar bonds and I fired all these rockets all at once, it's not going to go anywhere.
Right.
Nonpolar.
Right. Okay. Great. Thank you.
And then we learned that we could apply these same principles to more complex molecules, right? And then here's the difference in electronegativity that provides for the three categories of bonds. So what you should remember is 0.5, 1.7. Everything else is polar. And if it's polar, what do? You put partial charges on it. And that's how you get the dipoles. So then we applied that to different molecules. So we can see in formaldehyde is an excellent example because here's nonpolar bonds, right? No dipole. Here's the dipole. So you have a permanent dipole in formaldehyde. It acts like a little magnet. Same with water, right? So they're going to stick to each other. So we kind of did this one already. So CO2 is a symmetrical molecule. That's why it's nonpolar. There's nothing there to cancel out the carbon-oxygen dipole, so it's a polar molecule. And here's the schematic I tried to come up with after decades of trying to figure out how to explain this stuff. And then here was a scenario where we could understand how the different properties play out and basically govern how our world exists. So here's a whole bunch of different examples. Do you have any questions on any of these examples? Let me know.
We have sulfate, SO3.
Is one of these examples?
Yeah, I have here written down on my questions. If we could go through the Lewis structure on.
Okay, well that's, yeah. So here's sulfite right here.
Yes.
And here's sulfur trioxide. So I thought this was a really good exercise because you get different outcomes depending upon if you count your electrons correctly or not. So you want me to go through sulfite? Here's sulfite.
Yes. Yes.
Okay. So
Oh, it's written down, so I think it's self-explanatory. But I guess the double bond for sulfur trioxide, it doesn't matter where the double bond goes, right?
No, it does not. And that gives you 3 places to put the double bond, so 3 resonance structures.
Right, right. Okay. Okay, I think that's fine. What page is this on? This is 17. Okay, thank you.
17, yeah, 17. So I wouldn't worry about the exceptions to the rules. I'm just showing you that there are some. And of course, some people say that this is negative. Oh, you're so negative, showing people doing mistakes. It's like, I don't know. People nowadays are just so politically correct, it's absolutely ruining everything. Okay, so I go to the next chapter then?
Okay.
That was 10. Okay, so a lot of this was just review. So this is essentially a review right here. Again, showing you how the world, the way we exist, exists because of attractive forces. And we're able to predict this with the theories that we learned in chapter 10. So I reviewed the bond angles, right? And I know some students get confused. Well, how come you say it's a 120 when this page says it's a 116? Well, these are the actual numbers. This is theory, right? Here's some actual numbers, and the actual numbers are very close to theory. Many times are the same as theory. You need to know what the theory is. You're not going to memorize what is the bond angles in water, for example. Then expanded octets, I'm not going to test you on those. Resonance is a new to this chapter concept. So here in sulfur dioxide, I had to put the double bond there to make sulfur happy. If I didn't do that, it would not be a Battle-Lewis structure. But I could have put the double bond here, or I could have equally put it over there. If I did, I'd get the other resonance structure. So resonance structures differ only in where do you put the double bond. You cannot move the atoms, you're only moving where that double bond is. So I showed you a whole bunch of different examples of resonance. And like I said, my concept is I'll just show every example that you would normally encounter. I don't care whether it has to be on the test later on or not. I'm just showing you everything. Just like with the polyatomic ions, I just showed you all of them. So I know that when you're doing your homework, and maybe you're supposed to write the Lewis structure for aluminum, I should say ammonium chloride or something. Yeah, the ammonium ion is right there. That is the Lewis structure for it. I'm not going to hide the fact that it's more important to teach the stuff than try to find some way to test you on it. So I tried to tell you a little bit about each one because it really helps understand how things work. But I'm not going to ask you, these kind of questions, right? Let's see. A lot of it is like where they come from. Let's see. And then I just went and showed you all kinds of ones that obviously we didn't cover all of them, but we covered 90% of them. But all these, except for the ones you had to memorize in the other chapters, all these not going to be on the test. So there wasn't a whole lot in that chapter. Chapter 12 kind of had a lot of stuff in it. Come on, open. Man, the computer doesn't want to. Sharing all these screens, my computer wants to slow down, so I have to close them. Okay, so here's very simple. How do you know a chemical reaction happens? Just because you mix things together doesn't mean if something's happening. Could be nothing's happening. And I put this in this category, but in a red box because you know how to do this. But this is simply an application of it. But on the exam, and for Chemistry 100, I think I never did ask you to predict what the products will be of a reaction. Biochem course, yeah, they had to do that. So the reactions that you will have will be simple. I chose mostly simple ones because there's no reason in a general chemistry course numbered 100 where I'm going to have to find a way to make something really hard. There's no point in doing that. So here's some guidelines. Okay. So guidelines are just that. They're just guidelines. And I showed you in quite a lot of detail how to balance some of these reactions using these guidelines. And then at the same time, showing you examples of balancing, we showed you the 7 major categories of reactions. So by the way, since this is a review and you know that number 7 is redox, right? Where that would go? Somewhere. Oh, it's way down there. Anyway, I'll just talk about that as we go through. Are they redox reactions? So look at a synthesis reaction. Elements combining into a compound. Here, the oxidation numbers are 0, and here they're not. Yes, that's a redox reaction. Where do electrons go? They go from the least electronegative to the most electronegative. So electrons are going from the hydrogen to the nitrogen. So the oxidation numbers will be, hydrogen will be a +1, that's going to be a -3. In other words, hydrogen is getting oxidized and nitrogen is getting reduced. With a decomposition, a compound is decomposing into its elements, it's also a redox reaction. So here, oxygen is a -2, here it's a 0. So what's happening to the oxygen? Going from a -2 to a 0. Well, it's getting oxidized, right? No, reduced, no, oxidized. So here we're going from a +1 to a 0, so it's getting reduced. But to find out whether it's a redox, all I have to do is see, here's in a compound, here's an element, you know the redox number's changed. In double displacement reactions, we often use the solubility rules. You do not have to memorize them. But I put that there because it's chemistry. And I put it there so you realize in a later part of this chapter, why will this reaction happen? Because you formed a solid. It precipitated out of solution. That's what made the reaction happen.
And always during a reaction, just to clarify, you go from a more reactive substance to a more stable or less reactive substance.
Well, that's for a spontaneous reaction. So if you go to a power plant, right? Like H power, what are you doing? You're taking stuff with high potential energy and you're burning it. And it gives off energy, right? That's a spontaneous reaction. If you're making hydrogen and oxygen for a fuel cell, you're taking water that is perfectly happy, but then you're adding energy to split that water molecule into oxygen and into hydrogen. So that is not a spontaneous reaction. But if you now have a machine that takes the oxygen and the water and recombines it back into water, that is an exothermic reaction. So that would be a spontaneous reaction. So it's not like some reactions won't happen. They won't happen unless you make it happen by adding energy. And that's an exothermic reaction.
So if you add O2 to a reaction, is that exothermic?
O2, the molecule?
Yes.
In general, yes, because oxygen is so reactive. Mm-hmm. Likely that whatever happens on the other side would be less reactive than oxygen itself.
Okay.
Yeah. People don't realize that oxygen is extremely reactive.
What about cyanide? You know, when I was, I forget where the problem was, but I was trying to determine whether or not a reaction was a redox reaction. And I was I was looking for the oxidation numbers for carbon and nitrogen in cyanide.
Mm-hmm.
And I just wanted to confirm carbon is a -4 charge, right? And then the nitrogen is a +3.
So let's see, nitrogen is 3.04, carbon is 2.55, so nitrogen should get the negative charge,
Nitrogen.
and carbon would be positive.
So,
And it has to have a -1 charge.
right.
So it's possible that carbon in that case is doing the +2.
So carbon
In that
is the
case, it's a +2 rather than a +4.
and then nitrogen's the -3
Right. Uh-huh.
because it's more electronegative.
Exactly. Right.
Okay. Okay. Thank you.
So if we look at single displacement, so I just compared a double displacement with a single displacement. If you look at a double displacement, calcium didn't do anything to change its electron state, either did sodium, nothing did. But here in a single displacement, sodium went from a 0 to a +1. So sodium got oxidized. And lead went from a +2 to a 0, so lead got reduced. Okay, so it is a redox reaction. And by the way, would this reaction actually happen? Now, I'm asking you to compare the reactivity of lead to sodium. What do you know about lead? Well, it's a shiny metal. Use it for fishing weights. You can buy it at the store. You can do all kind of stuff with it. It may tarnish a little bit, get that powdery gray lead oxide on it, but it's there. It's fairly stable. But you can't go to the store and buy sodium. Sodium metal does not exist. It's too reactive. So here you see sodium way down here in the red, very reactive stuff. When you find sodium on planet Earth, it's always the sodium ion. So let me know if you have any questions as we're going along. Let's see, okay, neutralization reactions are actually double displacement, right? Molecule, 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 molecule. So they're not redox reactions. So we can spend our time with them thinking about not electrons going from point A to point B, but hydrogen ion. It's the definition of an acid. Acids have at least one hydrogen in front of their formula, and they donate H+. Bases, at this point, we only know that bases have hydroxide in their formula. And if you take H+ and OH- and put them together, they fall in love and make a very neutral and simple molecule, water. So this is reactive, this is stable. That's why the reactions happen.
Will a double displacement reaction always not be a redox reaction?
Right. Yep.
In all cases, yeah.
Yep. Mm-hmm.
Okay.
So then I showed you an easy way to balance these reactions by counting up the number of hydrogens available versus the number of hydroxides. Those two numbers have to be the same, right? Because every one of these needs exactly one of these. So when you do that, it's very easy to see how many water molecules you make. When I used to teach this in the regular way of doing it, students would often get this part wrong. Now they never get it wrong. So here's combustion reaction, simply reacting with molecular oxygen because it's so reactive. And finally, redox reactions, which we kind of covered on the way here. So on the exam, there will be a question, which one got oxidized? Which one is the oxidizing agent? They're not important, in terms of points, but they will be asked. So I'm looking at this problem right here, and I don't really need to put numbers exactly. But you see oxygen is very reactive, so it's going to take electrons and get a negative number. And what happens to the carbon? Well, it forms CO2 in water, so if oxygen is negative, then carbon has to be positive. So carbon went from a negative number to a positive number. Oxygen went from 0 to a negative number. So we can see that oxygen got reduced. Electrons flowed from the carbon to the oxygen. So if oxygen got reduced, what reduced it? Reducing agent. What could that be? Methane. Carbon got oxidized, so methane got oxidized. Who oxidized it? Oxygen. So what is oxygen in that case? An oxidizing agent.
And methane is the reducing agent.
Right.
Okay.
So at the same time, I was trying to summarize this as we were going through those examples. So just to summarize, right? Reactive going to stable will happen, is spontaneous. Stable going to reactive, not going to happen, not spontaneous. Now, that's confused by the fact that what do chemists do every day? We don't simply do what's already going to happen, right? We find ways to go in the opposite direction, called ingenuity. So here are some cases where a reaction will occur. So in this case with methane, it burns. You just know that. It's like gasoline, it burns. So that it's exothermic. Or if you actually saw the number over here as a product, it's giving off energy as a product. That's going to happen. Again, this is what the solubility rules told us. We don't have any rules for gases, so that makes it more difficult. So in your case, you just look for the symbol G, right, to tell you that you formed a gas, like here. So in this case, you probably know that hydrogen is a gas, but in other cases, you might not know. So you just look at, is there a G there? Here, you're not expected to memorize the solubility rules, but you know why there should be an S there, right? It's the solubility rules. In these cases, signal displacement, you're really comparing zinc and gold. Okay. Sodium and zinc. Let's say I'm looking at this reaction right here. What's happening? Electrons are going from the sodium to the zinc, right? So sodium is getting oxidized. Zinc chloride is the oxidizing agent. Zinc is getting reduced. Sodium is the reducing agent. And you're not expected to know that by just looking at these. You're looking at what are they doing. Because when you have the whole reaction, you're seeing here's where they started and here's what they're doing. So you're looking at the whole thing. So the last part of the exam will be this seemingly totally different kind of problem. So you need to know how to use the conversion factors. You need to know this nomenclature right here, the system of naming things. You need to know how to do this with the periodic table, right? So here's some examples of that. There guaranteed will be a question on this. Guaranteed there will be a question like that. And those are just kind of simple. They're not really necessarily conversion factors. They're just getting the data, right? Getting the numbers. Then they become conversion factors when you do problems. So for this exam, you're going to be able to, or be asked to do 1, 2, 3 types of conversions. And what's central to everything is moles. So here's the molar mass, converts between grams and moles, that's all it does. Here's Avogadro's number, converts between moles and individual particles, that's all it does. And here's moles of a molecule versus moles of an element. The conversion factor is simply the formula.
Excuse me, Professor. For the, I think on the previous page, with all the nomenclature like GW, AW, could you go over that a little bit? Because I'm not quite sure. I understand the difference between AW and GAW.
Okay.
I mean, what does the W represent?
Weight.
Weight, okay.
Right.
So
Oh,
here's
the reason why we use weight and not mass. So the number on the periodic table has no units. So we call it a weight.
right.
Now, I can apply units to it. If I use atomic mass units, 1 atom of oxygen is going to weigh 15.9994 atomic mass units. That's called the atomic weight. That's the weight of an individual atom.
Okay.
If I take that same number and I put grams on it, now I'm talking about a mole of those atoms. So that's the gram atomic weight, and that's also the molar mass. Molar mass for oxygen is 15.9994 grams.
They're all kind of, I guess, interrelated then between the atoms, the molecules, in those, in that chart on page 17.
Yeah, you mean here?
Yes.
Yeah, so if you're talking about atoms, right?
Hmm.
Like we were here, it's either the atomic weight or the gram atomic weight, which is also known as the molar mass.
And the only difference between the two is the unit.
Right,
Okay.
right. That's exactly what we did here. But then if you
Right.
got like a molecule, say like you got H2O, one molecule, the mass of one molecule would be called the molecular weight. So that would be one oxygen, which is 15 something AMU, and two hydrogens, each hydrogen being about 1 AMU each. So you're talking about around 18 AMU.
But if it was the GMW, then it would be 18 grams.
Exactly.
Okay.
Yep.
Great. Thank you.
And then we just use formula unit for ionic compounds. So anyway, I tried to go through with the second part of homework 15. I tried to go through important examples of this so you had experience doing it. Anyway, this is this other example, right? Let me just make sure this, yeah, okay. So you don't have a lot of examples and you don't need them. Because if you follow this, you're asked a question as a matter of, okay, I got 3 tools in my toolbox. Which one do I use first? It's one of these conversion factors. So if we look at one of these more complex ones, like how many grams of phosphorus and 6 grams of magnesium phosphate? Well, they're giving us the molar mass, so we don't have to calculate that. So I'm starting off with 6 grams of magnesium phosphate. That's what I got here. What do I need to do with that? What if I don't know anything what to do? I simply go to moles. Okay. So I know I got to get from grams of magnesium phosphate into moles of magnesium phosphate, so I did that. So what I'm going to look at the question again now, and it says, well, they want grams of phosphorus. So I don't have a way to go from moles of magnesium phosphate to grams of phosphorus, but I do have a way to go from moles of magnesium phosphate into moles of magnesium. That's this one, right? I just use the formula. I look at the formula, for every one of these, I got 3 magnesiums. That's my conversion factor. So they want phosphate in this case, phosphorus. So I got rid of moles of magnesium phosphate. For every mole of magnesium phosphate, there's 2 moles of phosphorus. So that gives me the moles of phosphorus now. Now what did they want again? Oh, grams. So I easily know how to get moles of phosphorus into grams. I just go to the periodic table. So that's how I got that. So I had to do 1, 2, 3 conversions to get to that final answer. Make sense? See how it works? So any other questions on this? Any other questions about anything in Unit 1? Is my microphone off?
I'm good. I've asked all my questions.
Okay, good. Anybody else? Okay, well,
No.
Yes. Oh, no. Okay, then I guess we'll stop it here. So I did record this. I'll load it up. I'll name it something. Don't know what I'll name it, but anyway. So again, if you need to take the exam tomorrow, just email me. I'll send you the password in the morning. Okay.
Thank you.
So you guys have
Otherwise,
a great day.
on Wednesday, we'll just email you on Wednesday for the Wednesday password, yeah?
Sure. Yeah. Sounds good. Okay.
Thank you, Professor.
Thank you. You guys have a great day.
You
See
too.
ya.